The cosmos is now more accessible to humanity than ever before, offering a level of precision previously unimaginable. With its unparalleled sensitivity and resolution, the James Webb Space Telescope, JWST, has revolutionized our ability to observe celestial objects, unveiling regions of a universe that had remained hidden in darkness for millennia. From ancient galaxies that formed only a few 100 million years after the Big Bang to the atmospheric compositions of distant exoplanets light years away, the JWST has become a sentinel of cosmic discovery. Among its most recent and astonishing revelations is the observation of a cataclysmic event involving Neptune, the most distant of our solar system's 8 planets. The telescope captured something extraordinary, a massive object colliding with the ice giant, sending shock waves through the scientific community and prompting new questions about the dynamics still at play in the farthest reaches of our celestial neighborhood. Neptune, named after the Roman god of the sea, has long captivated astronomers with its rich blue coloration, mysterious atmosphere, and extreme weather systems. Located approximately 4.5 billion kilometers from the Sun, Neptune is a remote, frozen world often cloaked in darkness and largely hidden from direct observation. Prior to the JWST, our most detailed understanding of Neptune came from the Voyager 2 flyby in 1989, which offered only a fleeting glimpse of its strange beauty. But now, thanks to the capabilities of JWST, scientists are witnessing the dynamic processes of this distant world in stunning detail. Neptune's supersonic winds, which can reach speeds of up to 2,000 km per hour, its immense rotating storms, and its faint ring system have long intrigued planetary scientists. However, this latest discovery, a high-energy impact event, has opened entirely new avenues for understanding not only Neptune but also the structure and evolution of the outer solar system. The event was first noted when astronomers studying JWST's infrared data noticed a peculiar and unprecedented anomaly in Neptune's upper atmosphere, a sudden burst of heat and energy. What initially appeared to be an unexplained fluctuation soon gained clarity when the telescope's imaging systems captured a distinct, bright infrared flash. The source of the disturbance appeared to be a massive object, a large asteroid, a giant comet, or possibly even a rogue planet, that had violently slammed into Neptune. The collision sent an enormous shock wave through the planet's thick gaseous atmosphere, creating visible thermal disturbances and a brief but detectable flash of light. Although the exact dimensions of the impactor remain uncertain, preliminary calculations suggest it may have been several kilometers wide, similar in scale to some of the largest known asteroids or the icy nuclei of long-period comets. Such an impact is exceedingly rare, especially in the far reaches of the solar system where planetary orbits tend to be stable and relatively free of the debris and gravitational chaos more typical of the inner solar system. That this object struck Neptune at all suggests it may have been pulled in by the planet's gravity from the Kuiper belt or, even more intriguingly, from the Oort cloud, a hypothetical distant spherical shell of icy bodies that surrounds the solar system. Another tantalizing possibility is that the impactor was a rogue planet, a planetary body ejected from its original star system that drifted through interstellar space until it was caught in Neptune's gravitational grasp. Throughout Earth's own history, collisions with large celestial objects have had dramatic consequences, including the asteroid that likely caused the extinction of the dinosaurs. Other planets such as Jupiter have experienced similar impacts, most famously the Shoemaker-Levy 9 collision in 1994. But for Neptune, a planet on the outermost edge of the solar system, this kind of cosmic violence has never before been observed with such clarity. The implications of this collision are wide-ranging. The massive energy released by the impact likely altered Neptune's atmosphere, which is composed mainly of hydrogen, helium, and methane. The shock wave would have instantly vaporized vast amounts of gas at the site of impact, generating atmospheric turbulence that could persist for years if not decades. Given Neptune's already extreme weather conditions, the infusion of new energy may intensify storm systems or give rise to entirely new atmospheric phenomena. The impact may have also disturbed Neptune's faint rings, which consist of tiny dust particles and are not well understood. Unlike the structured and reflective rings of Saturn, Neptune's rings are dim and diffuse. The force of the impact may have ejected additional material into orbit or disrupted the paths of existing particles, causing changes that could shed light on the origin, evolution, and stability of planetary ring systems across the solar system. Triton, Neptune's largest and most enigmatic moon, may also have been affected by this colossal event. Triton orbits Neptune in a retrograde direction, a rare feature that suggests it was not formed alongside Neptune but instead captured by the planet's gravity long ago, likely originating from the Kuiper belt. Triton is among the most geologically active moons in the solar system, with cryovolcanoes that vent nitrogen gas and icy particles into space. The seismic energy from the Neptune impact may have triggered tectonic shifts or intensified cryovolcanic eruptions on Triton. Should this prove true, it would offer an extraordinary opportunity to study the Moon's subsurface composition, internal heat sources, and its potential to host a subsurface ocean, a key requirement for life as we know it. If the collision was not an isolated event but part of a larger pattern, it may necessitate a re-evaluation of the gravitational dynamics and object migration pathways in the outer solar system. It could imply the presence of more large bodies in eccentric or unstable orbits, possibly posing future threats not only to Neptune but also to the inner planets, including Earth. JWST's role in capturing this momentous event cannot be overstated. Launched in December 2021 as the successor to the Hubble Space Telescope, the JWST specializes in infrared astronomy and is optimized for detecting subtle thermal signatures in cold and distant regions of space. Capturing this collision in near real-time illustrates both the telescope's technical capabilities and its power to reveal the ever-changing nature of planetary environments. In the coming months and years, scientists will continue to monitor Neptune, observing changes in its atmosphere, tracking any alterations to its rings, and scrutinizing Triton for signs of increased geological activity. The event also serves as a valuable analog for studying exoplanets, particularly gas giants that exhibit strange atmospheric or thermal characteristics. By comparing Neptune's behavior after the impact to data from other planetary systems, astronomers can refine their understanding of how exoplanets might respond to similar events. Additionally, this dramatic development could rejuvenate interest in launching a dedicated Neptune orbiter, a long-desired mission that could probe the planet's internal structure, atmospheric dynamics, and complex moon system with far greater precision. No spacecraft has visited Neptune since Voyager 2, and a return mission could yield a treasure trove of new insights, especially in the aftermath of such a transformative impact. Some researchers have even proposed sending a lander to Triton, which may now be experiencing increased geological activity. If Triton's internal heat levels have been elevated by the energy transmitted through the Neptune system, its potential subsurface ocean may become more dynamic, improving the chances of detecting life-supporting chemical processes or even microbial life. Studying Triton's response could also improve our understanding of the nature of captured moons and how their interactions with host planets shape their long-term evolution. The identity and origin of the impactor is perhaps the most intriguing mystery of all. If the object originated in the Oort cloud, this would mark the first confirmed observation of an Oort cloud body striking a planet, a historic milestone for solar system science. Debris from the impact might contain pristine material from the early solar system, preserved for billions of years in the icy outer regions of space. Alternatively, if a rogue planet was responsible, the implications become even more profound. Rogue planets are thought to be common throughout the galaxy, cast out of their home systems during the chaotic early stages of planetary formation. A documented interaction between a rogue planet and one of our solar system's members would mark a significant event in the study of planetary dynamics and interstellar phenomena. In this context, Neptune's collision becomes more than just a cosmic spectacle. It becomes a gateway into understanding the ancient history and continuing evolution of our solar system and others beyond it. The JWST has revealed that even in the cold, dim outskirts of our own star system, dramatic and transformative events still unfold. These are not mere footnotes in planetary history. They are pivotal chapters full of data and discovery that help scientists unravel the complex forces that shape celestial bodies. As data from the James Webb Space Telescope continues to stream in, offering deeper insights into this extraordinary collision, the astronomy community finds itself at the cusp of profound revelations, not just about Neptune but about the grand design of planetary systems, the risks and wonders of cosmic collisions, and the tantalizing possibility that life-supporting environments might exist in the most unexpected corners of our solar system. Future missions could capitalize on this remarkable cosmic incident by keeping a close watch on Neptune's atmosphere, its ring system, and especially the surface and geological activity of Triton. Scientists are particularly interested in monitoring for surface changes, cryovolcanic eruptions, or shifts in orbital dynamics that could have been triggered by the immense energy released during the impact. These after-effects are not merely curiosities. They represent critical data points that could lead to transformative insights about how outer solar system bodies respond to extreme events. As the James Webb Space Telescope continues to send back infrared images and spectral data, researchers will be able to track the progression of atmospheric turbulence across Neptune's surface, observe any evolving patterns in its complex weather systems, and even monitor for changes in cloud composition and distribution. Neptune, with its winds that break the sound barrier and storms large enough to swallow Earth, now becomes a laboratory where planetary science can witness evolution in real time. One of the most promising areas of inquiry lies in the potential for ongoing geophysical interactions between Neptune and Triton. Triton's retrograde orbit already suggests a violent past, likely the result of its capture by Neptune's gravity, and this recent collision may have triggered new levels of tidal heating within the Moon. If so, scientists might observe renewed cryovolcanic activity as internal pressure builds and forces subsurface material upward through fissures in the icy crust. Observations of nitrogen geysers erupting from Triton's surface could become more frequent or intense, offering researchers a rare opportunity to sample surface ejections and infer the chemical composition of its interior. The increase in thermal energy, whether from direct radiative transfer or induced orbital resonance, might even temporarily elevate the internal activity of Triton's hypothesized subsurface ocean. If such an ocean exists, and many planetary scientists believe it does, its dynamics could now be undergoing rapid change, potentially stirring up previously dormant nutrients or chemicals, some of which might support microbial life. Given that Europa and Enceladus, both of which show evidence of similar subsurface oceans and geysers, are considered prime candidates for harboring extraterrestrial life, Triton could quickly rise to the top of the list. This extraordinary Neptune collision therefore extends its relevance far beyond just one planet or moon. It opens the door to comparative planetology on a scale rarely achieved. The shock waves that race through Neptune's gaseous envelope are akin to seismic waves on Earth, and by measuring how these disturbances propagate, researchers may finally be able to infer details about the gas giant's elusive core. Whether it is solid, semi-solid, or fully fluid remains unknown, but current models suggest Neptune has a rocky core surrounded by a thick mantle of water, ammonia, and methane ices. Without direct observation, much remains speculative. A collision-induced atmospheric event of this magnitude provides a natural probe, allowing researchers to analyze how quickly thermal energy disperses and which regions retain heat longest. These observations, in turn, can refine models of density and structure that help not only with Neptune but also with understanding other gas giants, including those orbiting stars far beyond our own. At the same time, Neptune's faint, dusty ring system may become one of the most closely watched features in the solar system. The impact may have injected new material into orbit or destabilized existing ring particles. If the rings become brighter, more dispersed, or exhibit new arcs and clumps over time, it would suggest that ring systems, even ones as thin and subtle as Neptune's, are dynamic and highly sensitive to external stimuli. This could shed light on the longevity and sustainability of planetary rings, with broader applications in understanding exoplanets that exhibit similar features. Some distant exoplanets have been observed with rings many times the size of Saturn's, and unraveling the behavior of Neptune's rings following this collision might help decode the origin, maintenance, and evolution of those distant systems. In the broader astronomical context, this event has rekindled discussions about planetary defense and the hidden dynamism of the outer solar system. It has underscored how much we still don't know, and how many discoveries lie in wait, just beyond the veil of deep space.